Okay, this is the first workshop. We will do other workshop tomorrow. We will going to present our DOIT 3D micro, a plenoptic eyepiece for 3D microscopy. We are DOIT Plenoptic. We are a spin-off from the University of Valencia. We aim to bring 3D technology imaging for everybody, and we are working on developing products for 3D microscopy now. This is our team. We are young, but we have a strong foundation. We have two advisors from the university, Professor Manuel Martinez and Professor Genaro Saavedra. And we have 2 years to develop this system, this product, sorry. That, as you can see, can be attached to the eyepiece port of a microscope. Our technology is not based in a common lightfield imaging systems, in which typically the conventional lightfield imaging are based on, we have a main lens, and the main lens focus the image in front or behind the micro lens, or the other way is to focus the image in at the micro lens plane. In these modes, key factor to have a good system is to project the aperture of the main lens on the sensor, and the numerical aperture of this main lens needs to match the numerical aperture of the micro lens array. Otherwise, we will have a bigger field of view, and then the images will overlap, and or we could have a smaller field of view, and then to lose the resolution and parts of the sample. So this is the correct way. So matching the F number of the numerical aperture of the objective, the main lens, is the bottleneck of conventional light field microscopy, one of the bottlenecks of conventional light field microscopy, because this limits the number of objectives that you can work. We use a new way of capturing light field images. We capture orthographic views. In this case, we limit the field of view not with the aperture of the main lens, but with an independent field stop. The field stop and the object plane are placed at the focal length of the main lens in such a way that the rays are projected parallel towards the micro lens. This way, we can place the micro lens array in any plane and keep the image focused and the field stop in the proper size and plane. This approach of light field was implemented by Gabriele Scrofani in this setup, in which they use as a main lens an objective lens, an aperture stop, and an objective of a microscope, relay lens. This system does an image here, and then with an additional lens, the image are projected parallel towards the microlens array. So keeping this structure in mind, we thought, okay, we can, if we think in how the microscope is, the construction of a microscope is, and the optical path towards the eye is, we can think in, we have an objective, we have a tube lens that depends on the mark of the microscopes, and then we have the eyepiece and the eye. So we thought that we can move this toward this system, replacing the eye of the observer by the microlens array. So then this was the board of the plenoptic eyepiece. So this is our approach. We use the concept of an eyepiece to reduce the length of the system, to control the microlens relief, or in the case of the eye relief, and also to reduce aberration, chromatic aberration, and so to improve the quality of the images. It's very important to keep the microlens array in the exit pupil of the system to avoid this effect. And the great advantage of our system is that we can work with different objectives at the same time. We are not limited by the aperture of the objective, but we can work with different aperture at the same time. This is an example. For here we have 5 views in this aperture, and here we have 3 views for a bigger numerical aperture, but a smaller stop aperture. The price to pay is, if we have more views, we have worse spatial resolution, but bigger angular resolution. So after this brief introduction, we're going to show you how to work with this product, with this plenoptic eyepiece. Nico, please.
Okay, hello everybody. The first thing I wanted to show is that the setup of the device is really simple. I will share the screen. Here we have our microscope. The setup is really simple, as I was saying before. Once we have adjusted here our sample, we can select our field of view of interest, focus the sample as always, and then just remove one of the eyepieces of the microscope and replace it with the plenoptic eyepiece. Connect to the computer through the USB cable, and you can start to work with the plenoptic eyepiece. Okay.
Sorry. Well, what we do is as I said before, we need to adjust the exit pupil of the of the microscope to the location of the micro lens array and the sensor. So we have this system that moves the micro lens array and the sensor together in front or behind the exit pupil of the system. Okay, yeah. Okay, Nico.
Okay, let me share the screen. Once you have adjusted your sample, and once you have adjusted the position of the microlens array, we have to say that this an operation that you just have to do the first time you use your plenoptic eyepiece. Once you have adjusted this, you can start to work with the software. Here we have a beta version of our software. It's a really simple graphical user interface. What you see here basically is what you will see in the microscope, looking through the eyepiece. But as Angel was saying, our system has an increased depth of field by a factor n squared. We lose resolution, but we increase n squared times the depth of field. So what we have here is the sample, and with we can see it with an extended depth of field. The first sample we prepared, they are cotton fibers with a fluorescence dye. So we can start to work with the software. Here you have the camera parameter set. You can adjust the exposure time or the frame rate, or you can adjust the white balance manually, or you can do it automatically, and then you can start to work with the software. Here we can select fluorescence because we have a fluorescent sample. We are going to reconstruct the sample through this function. Here, what we are going to do is to focus at different planes of the sample, and the algorithm provides optical sectioning for this sample. So basically, using this slider, you can select at which plane to focus, and you can see different parts of the sample. You can do it. Moving the slider, or you can choose to select a fixed plane and moving the stage of your microscope. Focus the plane of interest.
No se te está viendo, Nico.
La pantalla.
Aquí no. La pantalla sí, pero aquí no.
Ah, sorry. So here, once you have seen let's say the depth range of interest of your sample, you can decide to save the focus tag here. Sample like this. Or with the same algorithm, the software is capable to save a point cloud of the sample, or calculate a depth map. The most important thing I think is that this algorithm works in real time. So you have optical sectioning in real time of the sample, and you can calculate the depth map in less than 100 milliseconds. We can now go and see the result. Here, for example, is the depth map, the normalized version of the depth map in color map, from blue the background to red the foreground, let's say. Now, once you have set the focus stack or the depth map, you can save the elemental images too, that are the different perspective views of the sample, and you can use all this information with our visualization software, for example. Now the problem we have is that they are, let's say, two separated software, but we are integrating them to have the visualization and the processing in one single software, let's say. So here, let me just copy paste the images from one folder to another. Here you can see the different perspectives of the sample. You can see what's behind and what's in front, and resolve the occlusions. For this sample, we are using a 20x objective. You can see there is parallax between the views. Or what's important too to say is that you can use the focal stack you saved or the point cloud. You can use them in not only in our visualization software, but you can use it in some other software like Fiji or some other software for point cloud visualization. I will show you with this sample and the other I prepared that you can use the focal stack, for example, in Fiji to get 3D reconstruction or to use some other things. Okay, let's switch to the other sample. You can let's say focus as you would with your microscope in the classical way.
No se está viendo la pantalla.
Or you can directly look at your sample here in the software. I have to switch to a 40x for this sample. Voy a apagar. Now with this sample, the problem we have is that with this microscope we are not able to illuminate with the right wavelength, so there is much background because we have to increase the exposure time and we have a lot of This sample is fat tissue. I think I didn't mention it before. And basically what you can do with Can you hear me now? Okay. I don't know from which point you couldn't hear me. But basically what I showed you was the same I showed you for uh, for the first sample. Okay. When you were talking about the fat tissue, the second sample I showed you, as I mentioned, it was fat tissue. We observed it with 40x. Here it is the sample. I had saved some elemental image from another portion. That the sample is very big, so I couldn't find the most significant, let's say, portion. But I had I had saved some elemental images. We had seen them before, and what I was saying before is that you can use Fiji2 with the information you saved from our software. You can use your Fiji as always. We saved some images from the fibers, for example. This is a focal stack from the fibers. You can use the 3D project to get the 3D reconstruction. Or you can do the same with the fat tissue sample. This is the focal stack. And this is a 3D reconstruction. These are the two samples we looked at before. Well, this is not the focus stack I say, but I can load it. Just give me 1 second. And I will load the focus tab we saved before. It's this one. And this is the corresponding projection. For the two samples we prepared for this workshop, I think that's all. But what I wanted to mention too, that is important, is that the device is capable to work with any illumination, so we can work with bright field too, and you can see some images from bright field. For example, we reconstructed a chip from a condenser of a chip, sorry. This is the reconstruction, this is the depth map of the chip with our visualization software. I can show you the perspective views too. This capture was done with a 10x objective. So we saw that we can switch from one objective to other with no problem. We used 20x for fibers, 40x for the fat tissue. This was done with a 10x. We cannot do it with this microscope because we cannot illuminate with white light in NEP illumination, but this was the result we obtained with another microscope. And I can show you one 3D point cloud representation that we captured with a commercial software. I think that it's all from my point. If there is some other time, I can show the video we captured with a live sample, with a living sample, sorry, but I don't know if there is some question before of the video. Thank you.
Hello, everybody. Can you hear me? Yes. Okay. Well, thank you, everyone, for watching this, attending this workshop. If you have any question, comments, or do you want us to clarify any of the aspects that Nico and Angel have been explaining, please feel free to write us, or if you want, we can also allow you to connect your camera and your microphone. So I think everything seems clear. We have, well, around 10 minutes if you want to solve your questions. So, well, feel free to ask whatever you think we can solve. We as I explained in the chat, we are now working to bring new samples in and to image those samples, to have more variety of samples in order to show you the performance. And well, this is something that is currently ongoing. It's a task that is currently ongoing. And well, if you, however, we are also open to conduct some pilot tests. So if you think you could be a candidate of having one of the first plenoptic eyepieces to collaborate close to us, like as an early adopter, do not hesitate to visit our website, to inscribe yourself in this early adopter program. And well, there are some seats left until the finish of this year, and we will open another early adopter program with different conditions by 2021, the first quarter. So you will be also able to participate at that point if you want. Okay, I think Amparo wants to ask a question. Hello, Amparo. Okay, sorry. I thought. Okay, you can disconnect if you want. I had like I've been notified by the platform by Hopin. Angel, we cannot hear you. You appear like muted. Your microphone is like crossed, red line crossed. Maybe if you re-enter, Nico, maybe if Angel re-enters, maybe we can now. I think we can hear.
¿Ahora?
Yes, Angel.
¿Ahora me oyes?
Yes, everyone can hear you.
Well, pues so we have not any question. People understood everything. Okay.
Have shy audience. However, tomorrow we will repeat the workshop. So because we have some technical difficulties sharing the screen, the audio, etc. So maybe if you want to step by and we can show you. Well, now Nico is showing like a book, I think. Because we can imagine living samples. So, well, this is something we will show you in the future, like 3D reconstruction of moving samples, in vivo samples. And well, if you want to step by tomorrow, we will repeat the workshop. We'll try to solve all the technical difficulties that we have faced today. And that's it. It's I don't know if Nico wants to show you anything, or we can close the session here. Nico, if you are talking, I cannot hear you. In fact, I think
Can you hear me now?
yes.
Okay, I had to go out to let the microphone work. No, I just was saying that this was the video I mentioned before, that I could show if there was some minutes left. It's just a demonstration that we can record living samples with our system.
That's right.
At the screen another time. This is the video. From this video, we just did a really simple reconstruction that was focusing at one plane and then focus for different frames and then focus and then refocus at different planes of the sample here.
I've seen
really simple reconstruction, just to demonstrate.
Okay, we can conclude here the workshop. However, I've seen the last like 10 minutes of the workshop when we finished, that there was like people that have joined the last 5 minutes. So if you want to come back tomorrow, we will repeat it at 4 Central European time, at 4 in the afternoon. So thank you everybody for stepping by, and thank you Nico and Angel for showing us the DOIT 3D micro plenoptic eyepiece. We hope to help a lot of microscopies for the 3D imaging needs in the coming months. See you soon. Thank you, everyone.
Thank you. Bye bye.
Thank you. Bye. Bye.
See
Bye.
you tomorrow.
See you tomorrow.
See you.